Hi, welcome back to es346 Basic Thermodynamics. This is module 1.4. The topic is temperature and pressure. The corresponding sections in the textbook are 1.8 through 1.10. We have three learning objectives in this module. At the end of this module, you will be able to define what is the continuum approximation. You will understand the macroscopic temperature-energy relationship, and you will understand the macroscopic pressure-force relationship. So first, let's talk about energy. We'll talk about molecular energy. Thermodynamics fundamentally is always interested in energy. And all energy is stored in molecules. So I show here, for example, a box that's full of a bunch of, let's say, they're gas molecules bouncing around. So each one of these molecules is flying in different directions. There's a certain amount of energy associated with all of those molecules. And if I wanted to know their energy, what I would do is I would end up adding up all their kinetic energy from translations of them moving, plus the energy associated with them vibrating, if they're a multi-atom molecule, and they might also be rotating. And if I add up all of that energy at the microscopic level, I'd have a total amount of energy. Now, although that's able to do that in theory, that's very, very cumbersome to do. And so what we would like to do is come up with a little easier way to do it. And that is the idea behind the continuum approximation, which says, I'm just going to go ahead and smear out all of those details, and I just want to know what the bulk average amount of energy is. And so if I did that, and was to know what the amount of energy is, I could actually measure that by putting in a thermometer. And that thermometer would read a particular temperature. And as the energy of the molecules increased, the temperature would increase. As the energy of the molecules decreased, the temperature would decrease. So therefore, temperature is a way to measure the total energy of all those molecules without looking at the detail. That is called the continuum approximation. I'm taking the details of the molecule and smearing it out into a continuum. Let's talk a little bit more about temperature. I just mentioned that it's a measure of the vibrational, rotational, and translational molecular energy. And that's true of gases, liquids, and solids. And the more they vibrate, the higher the temperature. So let's start off, look at something as cold as absolutely possible, which would be 0 degrees Kelvin. We would have a solid, and all of our molecules would be perfectly aligned, and they wouldn't be moving at all. Now, if the temperature was to increase a little bit to some temperature T1, which is greater than absolute Kelvin, the molecules would begin to vibrate back and forth and up and down, and also in the third dimension this way. And as the temperature goes up, they would begin to vibrate more and more. Now, I may go through a phase change. I could go into a liquid or into a gas, and they would begin to move further. They'd have more vibrational energy, more rotational energy, more translational energy. But instead of adding all of those up, each time we can just measure what the temperature is, and that will be a representation of how much energy is in our fluid. Let's talk a little bit about temperature scales. There's two temperature scales that we tend to use for two different energy systems. Two different unit systems, excuse me. The first is the SI system, where we have degrees Celsius and degrees Kelvin. And it's kind of convention not to use the degree symbol for the absolute scale. Correspondingly, in the English system, we have degrees Fahrenheit and then degrees Rankine, where degrees Rankine is the absolute scale. So if we think of this kind of drawing a vertical of temperature increasing as I go up, if I had my Celsius scale, I would have 0 degrees Celsius here. Or I could be using an absolute scale, where I would have 0 degrees Kelvin down here, which would correspond with minus 273 degrees Celsius. Analogously, for the English system, where we have degrees Fahrenheit, we could have 0 degrees Fahrenheit there. The absolute scale, which starts lower, we have 0 degrees Rankine here. And that corresponding number there is minus 460 degrees Fahrenheit. Both of these conversions are in your book, and you don't need to memorize them, but I bet you do by the end of this class. All right, we talked about temperature. Let's talk about pressure now. And pressure, if you remember from physics, is a force per area. So again, we have this box of molecules bouncing around, flying in various directions. And you can imagine if I was to measure the force over here when all these molecules come and hit the edge, I would have a particular force per area as each molecule comes and bounces off of this particular section of the wall of this tank. So that's associated with both the momentum of the molecules and the number of molecules that I have. So again, I could go ahead and do a continuum approximation where I'm just going to sort of smear out the whole area, not count up all the molecules, and I'm going to actually measure the pressure. And I could do that by attaching a pressure gauge, which is measuring all of those impacts and giving me a certain value of the pressure, which is related to the amount of momentum inside the gas and the amount of material that I have. So similar to temperature, there's different pressure scales. In the SI system, we'll talk about pascals, or often we'll talk about kilopascals, or 1 kilopascal is 1,000 pascals. And then in the English system, we tend to use just PSI, which is a pound force per square inch. Now, again, like temperature, you've got absolute scales and relative scales. And so if I was to go ahead and look at, for example, 0 pascals, that if I talk about it as a gauge pressure, where this is PATM, there would also be an absolute scale that starts down here. So in the SI system, we may specify a pressure as, for example, 20 pascals gauge or 20 pascals absolute. In the English system, it's a little different. Again, I've got both a gauge system and an absolute system. And here what we use is PSIG and PSIA for absolute versus gauge. And the difference between that right there is atmospheric pressure, PATM. That's about 14.7 PSIA, or about 101 kilopascals. We'll look a little bit more at pressure. And remember, pressure is all the force of all those molecules hitting. Now, if I was to look at a fluid, like, for example, water, as I move down in the fluid, I've got more and more material that's hitting me on top of it, and so the pressure goes up. And we know what the pressure is as the density of the fluid times gravity times how far down I've gone, or I call that H. So the pressure increases as I go down, as shown in the diagram there. But it doesn't increase as I move across. So all of these points have the exact same pressure. Pressure only changes if I go up or down because I'm having more or less material above me. Okay, let's go ahead and do a numeric example with pressure using that concept of pressure increasing when I go up and down, but not increasing when I move back and forth. So here's the question. What I want to know is, what is the pressure in this tank? I've got air here. And what I do know is the distances of these different fluids. So if you look closely, you'll see I've got water in blue, and then I have oil in yellow, and then I have mercury in this gray here. So I've got 3 different fluids in here. This is called a manometer. And what I want to know is, what is the pressure in here, knowing that the pressure outside, the atmospheric pressure, is 100 kilopascals. Well, the way I'm going to solve this is I'm going to say, well, I'm going to start off with my 100 kilopascals, which is the pressure right there, and I'm going to go ahead and imagine you're like a scuba diver. I'm going to go ahead and dive down to a depth of H3 through this mercury. The pressure would go up, so it's going to be 100 kilopascals plus the density of the mercury, gravity, times the H of the mercury. That's H3. Now, I can go ahead and move across with no change in pressure, so we just might imagine we're able to transport ourselves right over to that interface right there. And now I'm going to go ahead and swim upwards through the oil, which is going to give me a decrease in pressure. So I'm going to go minus the density, gravity, this is H2, and that's going to be a decrease in pressure. And now I can go ahead and swim right across over here into the water. And in fact, now what I'm going to do is just go ahead and keep moving into the tank. As long as you're moving laterally through the same fluid, the pressure isn't changing. And so what I'm going to do now is go upwards. So I'm going to go minus rho g H1, and that is of the water. And that is going to be equal to the pressure at point 1 that I'm looking for. Okay, so let's go ahead and plug some numbers in here. And so I'm starting off with, here's my atmospheric pressure of 100 kilopascals. I've converted that to 100,000 pascals to move it into primary units. And now I have the properties of mercury here. So 15 kilograms per cubic meter. That comes to my 15 grams per cubic centimeter. This is gravity here, and there is my H3 value, converting that to meters. Then I subtracted the properties here. Those are of the oil, and then subtracted the properties there that are of water. And every time I've converted these to primary units, kilograms and meters, that way I'm going to be working, that'll be the same units as Pascal. If I go ahead and do all of my arithmetic, I can find out what the answer to that is, and it's 120,580 pascals, or 120.58 kilopascals.